You might have a problem in 3 dimensions that has just one constraint, in which case the constraint is just some surface that you have to remain on. But if you're in 3 dimensions, you could also have a situation where you have 2 constraints, right? So if you're in 3 dimensions and you have 2 constraints, then that leaves behind some kind of one-dimensional object that would be the intersection of 2 surfaces. So what do we do in that case for the method of Lagrange multipliers? Well, your 2 constraints are 2 surfaces intersecting in some curve. So you're along this curve, and you have to move. To stay on this curve, you have to be moving perpendicular to both gradients. So there's a gradient for the first surface and a gradient for the second surface. And in order to stay on both surfaces, so to stay on that intersection, you have to be moving perpendicular to both of those gradients. Now, as long as the gradient of f doesn't lie in the plane created by those 2 gradients, then you can move a little bit in the direction, sort of partially in the direction of the gradient of f, and so you can get some increase in your output function, or if you're moving the other way, you could get decrease. But once you get to a location where the gradient of f lies in the 2 planes created by the gradients of the constraints, then the only way you could increase f or perhaps decrease f is by moving in a direction that would carry you off of either moving partially in the direction of the gradient of G2, which would take you off that constraint, or partially in the direction of the gradient of G1, which would take you off that constraint. So when you get to a max, then what you're going to see is that the gradient of f is at least some part in the gradient of G1, or some portion in the direction of the gradient of G2, or some combination of those. And so the only way you could actually move in the direction of that gradient you'd have to move perpendicular to the gradient of G1 or gradient of G2, and that's going to carry you off the constraint, and so you can't really go any further with your maximization or minimization of f. So the way we write that constraint is that the gradient of f lies in the plane created by the gradient of G1 and the gradient of G2. In other words, gradient f is just a combination, a little bit of gradient G1 and a little bit of gradient G2, and so gradient f lies in that particular plane. Let's look at an example of how we could use that. We've got this function, and we have to maximize that function subject to these 2 constraints. First, x plus 2y plus 3z has to equal 6, and x plus 3y plus 9z has to equal 9. We're thinking this is our first constraint, g1 of x, y, and z, right? And the constraint is just that g1 has to be equal to that constant. And here's our other constraint, g2 of x, y, and z, and it has to be equal to the constant 9. Okay, so the condition for us to have a max or a min is that the gradient of f has to be in the plane created by the gradient of G1 and the gradient of G2. Another way of saying that is gradient f has to be built out of a little bit of gradient G1 and a little bit of gradient G2, or one or the other. Okay, so let's find gradient of f. In this case, the gradient of f, the partial with respect to x is 2x, the partial with respect to y is 2, and the partial with respect to z is negative 2z. And that's got to be some scalar times the gradient of G1. Gradient of G1 is 1, 2, 3, plus some other scalar mu times the gradient of G2, which is 1, 3, 9. And this gives us 3 equations. 2x equals lambda plus mu, 2 equals 2 lambda plus 3 mu, and negative 2z equals 3 lambda plus 9 mu. Now there's 5 unknowns here, so we still don't know x, y, and z, or mu, or lambda, so we need 2 more equations, but of course the constraints have to be satisfied, and so that's where we can get our 2 additional equations that will allow us to solve for all 5. Okay, so we have to solve this system of 5 equations and 5 unknowns. In this case, it's a linear system, so we could set it up as a big 5x5 matrix or a big 5x5 system of equations and use Gaussian elimination to solve that linear system. We could also, this one is simple enough that we could do it by hand. The first thing that we could do would be maybe to combine these two equations to solve for lambda in terms of x and to solve for mu in terms of x, because if I take negative 2 times this equation and add it to that equation, the lambda will disappear. If I do that, I get 2 minus 4x, because I took negative 2 times 2x and added it to 2. Negative 2 times lambda plus 2 lambda would be no lambda, and negative 2 times mu plus 3 mu would be mu. So now I have mu in terms of x. That's a little step forward here. And I could also do the same thing, except for I could eliminate mu. If I take negative 3 times this first equation and add to the second equation, mu is going to disappear. So negative 3 times 2x would be negative 6x plus 2, so that's 2 minus 6x. And negative 3 times lambda plus 2 lambda would be negative lambda. And then negative 3 mu plus 3 mu would be no mu. So I have now mu and lambda in terms of x. My next step will be to solve for z now in terms of x, because negative 2z is equal to 3 lambda, but 3 lambda would be 3 times 2 minus 4x, so that would be 6 minus 12x, and 9, did that just a little bit wrong. Let's see. I should probably finish this off. Lambda is 6x minus 2. Okay, now negative 2z is equal to 3 lambda. I used the wrong equation before. 3 times lambda would be 18x minus 6, and 9 mu. This is the equation for mu, so 9 mu would be 18 minus 36x. Okay, now I can solve for z. If I divide by negative 2, I get z equals negative 9x plus 3. 18 divided by negative 2 would be minus 9, and negative 36x divided by negative 2 would be plus 18x. So now I have z in terms of x as well. Let's see, if I could combine like terms here. 18x and minus 9x is positive 9x, and 3 minus 9 is negative 6. So far I have 3 of my things, mu, lambda, and z. In terms of x, I can now I haven't used these two equations yet, so I could use those two equations to get, let's see, I could get y in terms of x, because x plus 2y plus 3z, but 3 times z would be 27x minus 18. That has to equal 6. So x and 27x would make 28x, and we'd have 2y. And we could move this 18 over here. 6 and 18 makes 24. So we have 14x plus y equals 12 when I divide both sides by 2. So y equals 12 minus 14x. Now I have y in terms of x. I can finally now solve for x, because if I plug into this last equation, we have x plus 3y. The 3y would be 36, and 3 times 14 is 42, so minus 42x plus 9z, but then 9z is 9x minus 6, so that would be 81x minus 54. That has to be equal to 9. Now I have an equation with x alone, so I can pick up the value for x. Once I have x, I can find y, I can find z, and that pretty much gives me my location. So let's see, we have 81x, or actually 82x, and we take away 42. That's going to leave 40x. So that took care of this term, and this term. And then we have 30. Let's see, 54 plus 9 would give us 63, and we take away 36. Let's see, 63 take away 36 is going to leave us, 27. So 40x equals 27. So x equals 27 over 40. There's our x coordinate. Now that we have x, we can go ahead and pick up y, y and z. So y is going to be 12 minus 14x and z is going to be 9 times x, which would be 27 over 40 minus 6. So now we could simplify that, but we see that from our method of Lagrange multipliers we had two constraints, and we're able to find the point on the line defined by these two constraints where this is maximized.